Okay, welcome back everyone. Today we have Aslak Buan and he's going to tell us about on wide subcategories.
Thank you very much. And first, thanks to the organizers, both of the program and of the seminar, for inviting me. I'm very happy to be here. Would like to be even more here in the sense that I'm 500 meters away from the seminar room with a sore throat and coughing a bit. So that's why we do it this way. Okay, so I will talk today about some joint work with recent joint work with Eric Hanson, but it builds a lot on earlier, quite recent work with the Bethany, which I also will say quite a lot about in this talk. Okay, so our setting is finite-dimensional algebras, and we are interested in this sort of trinity here with involving tilting, toe tilting theory, torsion classes, and the theory of wide subcategories. So what does this have to do with the cluster theory? So it's a long story, but I'll make a quite short version of it. So in the first attempts in categorifying acyclic cluster algebras were done by trying to model clusters using tilting modules in hereditary algebras. So a precise version of it was given by cluster categories, but it really boils down to understanding tilting theory for hereditary algebra in the acyclic case. That captured a lot of the combinatorial properties of cluster algebras, and this has later been generalized to many nice classes of algebras, so like Jacobian algebras, cluster tilted algebras, two-Calabi-Yau tilted algebras, and so on. But if one really wants to do something similar to cluster combinatorics for any finite-dimensional algebra, then it turns out that toe tilting is sort of the right setting. And this was pointed out in work by Adachi, Yama, Rayton almost 10 years ago now. So it was, I guess, 2012. Their paper appeared as a preprint. And yeah, okay, before we go on to that, also toe tilting is tilting in the hereditary case. And in the hereditary case, then already in 2006, in the beautiful paper by Ingalls and Thomas, it was pointed out the nice sort of interplay between the tilting theory, or in their setting, support tilting modules, torsion theory, and wide subcategories. It was they gave very precise correspondences between these three different theories. And in the toe tilting setting, the interplay with torsion theory was evident already from the start and explicit in the papers of Adachi, Yama, Rayton, while the wide subcategories somehow entered the scene a little bit later, and coming from many different sources. I will make some of them a bit explicit now, and giving you some motivating theorems for what we're doing, but it's still not quite absolutely well understood, sort of the interplay between wide subcategories and these two other directions that I'm mentioning here. Okay, so that's so one of our motivation is to better understand the interplay of these three theories. The other one is, the other motivation is to look at a categorical structure. You look at a category, special category, where the objects are the wide subcategories. This is connected to several things, among other things, the tau exceptional sequences that Bethany was talking about in a seminar here a few weeks ago, and also to the picture groups that Gordana told us about last week. Okay, so let's fix some notation before we proceed. So my algebra will always be finite dimensional, and I call it lambda. I deal with finite dimensional modules. Mod lambda is the category of finite dimensional, well, left or right modules. And then I use this perpendicular notation. So x perpendicular means either for an object x or for a category, a full subcategory x. It means all y such that there's no homomorphisms from any object in from x to y, where if x is a subcategory, it means from any object in x. And then we have this gen m, which are for a module m, it is all modules x that are generated by copies of m. So that's gen m, and then tau is always the Ostrander-Ruyten translate. So that's the main notation I will use. And then we're especially interested in the sort of the nice categories in these settings. Yeah, I should say that all, when I talk about subcategories, they are always full subcategories. They are always closed in their isomorphism. And usually I only consider objects up to isomorphism. But the nice categories that we will look at, they are often functorially finite. We just call it FF, functorially finite, which you can think about in some sense finitely generated. More precisely, it means that we need the existence of approximations. What does that mean? So for any object y, we say that x is functorially finite if we have an object x in the category x and a map from x to y, such that any map from x from any object in x to y factors through this fixed map from x to y. And this is a right approximation. Then there's a dual notion of left approximation, and a functorially finite subcategory. It has both left and right approximations for all objects in one. So these are the categories we are especially interested in. Okay, and let us define or these three concepts that I mentioned. So we have tau rigid pairs. So these are whenever you have a tau rigid module. So tau rigid module just means that you have no morphisms from m to tau of m. Also called, so that's a tau rigid module. If you in addition have a projective module P such that there's no maps from P to M, then you can call M, P a tau rigid pair. So two modules, one is projective, no maps from P to M, and M is tau rigid. Then we have the concept of torsion classes. We can think about them as just full subcategories which are closed under factors and extensions. And then so they and then in particular the functorially finite torsion classes, those are exactly those torsion classes which are generated by a tau rigid module. So they are gen m for a tau rigid module. And in fact, in Igusa-Todorov'sdefinition paper that I mentioned, they give a stronger statement. They show that there is a correspondence between certain tau tilting pairs, namely the so-called support tau tilting modules, and the functorially finite torsion classes. So a support tau tilting module is a tau rigid pair, which is maximal in the sense that if you add up the number of summands in M and P, then this is the same number as the number of simple lambda modules. Okay, so those were torsion classes, and then we have wide subcategories. So these are exactly subcategories which are closed under kernels, co-kernels, and extensions. Equivalently, they are subcategories which are abelian and exactly embedded in the module category. So these are the wide subcategories, And a wide subcategory, so it's especially it's an abelian category, and it is a module category exactly when it is functorially finite, which is again the same as saying that it should have enough projectives, and then it is actually isomorphic to the endomorphism ring on these projectives. And I don't know actually who to attribute this last statement to. There is a proof, an explicit proof in a recent paper by Asai, but I think this is some fact which has been around for a long time, and I'm not sure actually where to trace it to. Okay, so that are the three main actors: rigid pairs, torsion classes, and wide subcategories. So now I'd like to give two motivating theorems. It sort of shows where the wide subcategories enters the stage. The first one in the form I've stated it here, it is by Demonet, Iyama, Redding, Rayton, and Thomas. The meeting of the theorem is really in a bit earlier paper of Jasso. So therefore, I use this notation J for these special categories. It would be less convenient to use DI or RT, so that's good. We can use J for what I call the toe perpendicular wide subcategories. So they are given by starting with the toe rigid pair in mod lambda, MP, and then we take this orthogonal in this sense. So we take all the objects which has no maps from M, no maps to tau of M, and no maps from P in addition. I could mention that Jasso only considered this kind of categories, and then in the 5-author paper I mentioned with Demonet and more, then they also considered this slightly more general setting. So such tau perpendicular categories, they are actually equivalent to module categories for some finite dimensional algebra. So this is one part of the theorem. And the other part of the theorem is that such categories sit inside the big module category as a wide subcategory. Okay, and now if one combines these two facts, so that this is a wide subcategory and it's equivalent to a module category, then that means exactly that it is functorially finite wide subcategory by the statement on the last page. And we should also note that a special case, if you take M to be 0, then this first part here just vanishes. We're left with P perp, and that's exactly a Sire subcategory. So Sire subcategory is stronger than the wide subcategory. It's closed under factors, submodules, and extensions. And you can think about Sire subcategories exactly those you get if you think about the quiver algebra. The Sire subcategories are the module categories you get by just killing a number of vertices from your algebra, right, which corresponds to these projectives, P. So last thing I want to note is that in the case we're dealing with hereditary algebras, then this Jasso perpendicular or this tau perpendicular JMP is the same as the Geigle-Lenzing perpendicular subcategories, which have been around for a long time, since the 80s, I guess, or maybe early 90s. No, I think 80s. And which, yeah. So why is this? So this condition being perpendicular to tau M, if you use the Auslander-Reisten formula, this can be translated to an X1 vanishing condition with M. So X1 M blank vanish if and only if hom blank tau M vanish by the Auslander-Reisten formula. So therefore this can be this is the same as a Geiger-Lenzing perpendicular, which is saying that both hom and X with M should vanish. Okay. So these are this is one of the motivating theorems. So we this is where the tau perpendicular subcategories come from, and I should mention that there is another proof, I guess, that this is a wide subcategory in work by so I guess it's independent proof in a paper by Brewster Smith and Treffinger, where they consider connections with these wide subcategories and stability conditions and this wall and chamber structures and so on. Yep. So the second theorem, which I want to stress, is this, which in the form I'm stating it here is by Marks and Stoviceck. It was proved a more a stronger version of it was proved in the hereditary case in the paper of Ingalls and Thomas that I mentioned introductory. So it somehow connects wide subcategories with torsion classes. So I'll try to decode this diagram. So if you fix some finite dimensional algebra, we can, from any wide subcategory, we can extend it to a torsion class by first, or wide subcategory is V. We first take all objects which are generated by V, and then we extend by taking all objects which has filtrations in Gen V, meaning that you have filtration where all subfactors are in Gen V. So this produces, from a wide subcategory, a larger torsion class. Then you can go the other way, start with the torsion class, and inside there you will find a wide subcategory. Namely, you take exactly those x in T, such that whenever you have a map y to x, where both y and x are in T, then the kernel of f should also be in T. So this will be a subcategory of T, and it is a wide subcategory. So these maps are nice. In particular, the maps going here, map going from left to right is injective. So if you go first right, then left, it is the identity. But in general, there are not bijections. However, if you restrict now to here only the functorially finite torsion classes, then the map going from right to left is injective. So, so you produce then a subset of wide subcategories, so that since you have an injective map here, we can identify the image of that map. We call those left finite wide subcategories. I think this name was first given by Asai. So a left finite wide subcategories is then exactly a wide subcategory such that the corresponding torsion class is functorially finite. Right, by this using that this map is a bijection and and we know the inverse. So it is then not so hard to see that if you have such a wide subcategory such that Gen V is functorially finite, then this subcategory itself is also functorially finite. So you get an inclusion here. So the left finite subcategories is a subset of the functorially finite subcategories. Okay, so one of our motivations is to understand how does, if you look back at our two perpendicular categories, how do they fit into this picture? Where are they on the right, on the left side here? Right. Okay, and then let's have a look at this category that I mentioned. I try here to make a very, I think this is in some sense a fancy category, so I try to draw a fancy W. It wasn't that fancy. It's easier in LaTeX to make some fancy symbols, but this is the name of the category. So this category, which was considered by to get in joint work with Bethany in the tau tilting finite case, it was earlier studied by, or the idea comes from Igusa-Todorov, who studied this kind of category in a hereditary case. What is special about toe-tilting finite algebras? Well, I haven't defined them. It means that there's only a finite number of toe-tilting modules, or equivalently, there's only a finite number of toe-rigid modules, actually. In that case, all the wide subcategories are actually toe-perpendicular. This is not so hard to see, but these are, yeah, and I guess it is explicitly also in the TIRRT paper, like that. In this case, all the wide subcategories are toe-perpendicular. So when defining our category W, the wide subcategories are the objects. And if you fix a wide subcategories, then the maps that goes out from this object are given by taking toe-rigid pairs in W. So you take a toe-rigid pair in W. And now, where does that map land? It lands in the toe-perpendicular category, which is associated with that toe-rigid pair. Here, it's very important to note that, well, why can we talk about a toe-rigid pair in W? Well, because it is a module category, so there is a toe. There is no slender rate and translate, because we already know that the toe-perpendicular categories are module categories. But what is important is that this tau might be different from the tau in the big module category, right? So when I talk about the toe-rigid module in W, I mean something which is toe-rigid with respect to the Auslander write and translate in W, not the Auslander write and translate in the big algebra in mod lambda. Right, so there are modules which are toe-rigid in subcategories, but they're not toe-rigid in the big category. And also modules can be projective in this subcategory, even if they are not projective as lambda modules. All right. So all this is relative to the subcategory U, where this object where they live. So for each pair MP which is toe-rigid in W, you get such a map. Okay, and in particular, we get some irreducible maps exactly when this pair is indecomposable. And what do I mean? I mean that then either M or P is 0, and the other one is an intercomposable module. And then the map is irreducible in the sense that if it factors through something, it must, if it factors through two maps, then one of them must be the identity map. Then we struggled quite hard to actually prove that this is a well-defined category. It's not at all obvious because when you want to compose, it's not obvious how to compose things even. Because now if you want to take a new map starting in this subcategory, then that would be given by a toe-rigid. If you want to take this map and compose it with a new map starting in W prime, then you would like to have a toe-rigid pair in W prime. But this module is not toe-rigid here, so it's not clear how you could define a composition of that reason. So you somehow need to lift those toe-rigid objects here to, in a unique way, to something toe-rigid here. So I'll come back to that perspective in a little while. But these are then one of the things, or one of the reasons we want to better understand these toe-perpendicular categories is that they are they naturally turn up when trying to look at this category of wide subcategories. Yeah, and some comments about this category. One is that, well, if you have an indecomposable projective, so a module which is projective in a wide subcategory V, then you could look at two different pairs. So these are two different tau-rigid pairs. Either P, I mean the projective is tau-rigid, but you can also think about this object. That would lead to two different irreducible maps from V to P perp, since P perp is both the Hasso perpendicular of P0 or of 0P. So this category somehow contains more information than just the sort of the Hasso diagram of wide subcategories. You sometimes get double arrows, which plays an important role for this category. Actually, double arrows comes whenever you have projective objects. And then to try to relate it to the signed exceptional sequences. So now, yeah. So now the notation here is a bit sloppy. But if you start with mod lambda and then take T1, so then you want this to be an indecomposable tau-rigid pair. That means it's either a tau-rigid module or it is somehow 0, P for a projective. Right, so this T1 is an indecomposable tau-rigid pair. So it's one of these two. And then if you take a composition of such, starting with mod lambda and going down to 0, this then gives exactly what is we have named as a signed tau exceptional sequence. Starting with sort of, yeah, it's ending in T1, starting in Tn. So this is a way to define one way that signed tau exceptional sequences can be defined. And the signs come from the fact that some of the TIs can be of the form 0P, right? Then you get some of a sign. Right? So if all those were actually tau-rigid modules, it would somehow be an unsigned tau exceptional sequence. Okay? And then I think, so the reason, I guess, that so Igusa-Todorov defined this category in the hereditary case. They wanted it to relate it to the picture group Dana told us about last week, and not be very precise here, and please don't ask me about the details. This is sort of beyond where I feel competent, but if you start with this category, you can take somehow form a topological space called the classifying space. So basically it's you make a simplicial set where the n simplices are compositions of n composable maps. You make this into a topological space. You take fundamental group of this space, and this gives you the picture group in the hereditary case. And then Igusa Hanson showed that you have a similar construction in the tau-rigid finite case. Yes, with that definition of the category of wide subcategories. Okay, so this also relates to that construction. Okay, so then let us now look at the different wide subcategories which have appeared so far. First we have the set of all wide subcategories, and as I mentioned, we're especially interested in those which are functorially finite. Then we have the tau perpendicular subcategories, which we have already noticed that since they are equivalent to module categories, they are functorially finite, so we have inclusion here. Then it is somehow implicit in Marks-Stoviceck and made explicit in a paper by Igusa that the left finite ones which I mentioned, those are the ones which correspond to functorially finite torsion classes, or finitely generated torsion classes, if you wish. They are in particular tau perpendicular. then I forgot to mention that there is a dual concept of right finite wide subcategories. Well, these are exactly those which correspond in a dual way to the left finite ones. They correspond to finitely generated torsion pairs. The right finite ones, they correspond to finitely generated torsion-free classes in a dual way. I will not give any details there, but these are two in principle different classes of 5 subcategories. And here on the bottom, we have these very special side subcategories, which you get by just killing some projectives or some vertices in your river. And let me see, and we have already pointed out why we have inclusions here, and this is just dual, that these two inclusions here are both proper. That can be, well, so there's an example in a paper by Asai in the semi-bricks, and the paper called semi-bricks, and they extend that example slightly in our paper, me and Eric, and together this shows that both these inclusions here are proper. The problem is somehow, well, let me get back to that. Yeah, I should mention that in the case lambda is hereditary, then both 2 and 3 are equal. So then all these categories here are the same. And it is actually for those wide subcategories here that one has this category of wide subcategories. While in the tau rigid finite case, actually all these are the same. So both 1, 2, and 3, and also this are equal. And maybe it's want to note also that if one has a local algebra with only one vertex algebra, then there are not many wide subcategories. There is only the 0 and the full model category. Right. So what is special or what is interesting about these left finite subcategories are that they're not closed. Remember that all this is in particular the wide subcategories here, which are functorially finite, they are module categories. So we can talk about side subcategories of this. But the side subcategory of a left finite one is not necessarily left finite. And that's somehow the main idea of the proof of the first main theorem you have together with Eric. It's that, well, it's actually sufficient to close this left finite up under taking side subcategories. So the theorem says that if you have a wide subcategory, then it is tau perpendicular if and only if it is left finite, if it is a side subcategory of a left finite wide subcategory. And then I mentioned also that, well, there's a dual concept of tau inverse rigid modules, and then it's a natural way to talk about tau inverse perpendicular subcategories. We show or we point out that this concept is self-dual in the sense that a wide subcategory is tau perpendicular if and only if it's tau inverse perpendicular. This is almost by definition. And then using results of Asai and Pfeiffer, we can also classify or characterize these tau perpendicular subcategories by this condition D, saying that they are intersections of a functorially finite torsion class with a functorially finite torsion-free class, with the property that T perp is in F. So this is our first main theorem, but our contribution to it is really to fit in the tau perpendicular subcategories here. While B and D and also C, which is dual, is basically in the side of Piper's paper. Okay, so so this is a characterization of this perpendicular subcategory. And then let's return to the category of sorry. Sorry about that. Let's return to the category of wide subcategories, which now we want to study for any finite dimensional algebra. And then it's not longer the category of wide subcategories, but it's the category of tau perpendicular wide subcategories of mod lambda. So you restrict, you don't remember that in the tau rigid finite case, it's really all wide subcategories, but in the general case, you only want to consider those which are tau perpendicular. They turn up naturally because you want to generalize the way we form maps in this category. Right, so again, the objects are tau perpendicular wide subcategory, and then if we start with an object W, we can form maps to other perpendicular wide subcategories exactly when this one is given as the tau perpendicular subcategory associated to the tau rigid pair MP. So remember, tau rigid pair means tau rigid module and a projective module now in the category W. And again, it's not at all clear that this is well defined. It's not clear how to define compositions. It's not clear that, and when you have defined composition, it's not clear that it is associative. Right. So let's look at the main steps in actually proving this. So there's three main steps. So the first step is we somehow need to lift when we have a map. Let's look back here. When we have an object here and we want to compose this map that we have here with a new map, we need to be able to lift those tau rigid pairs in W to something in in W prime to something in W. So this is somehow what the first step is that there is a bijection, we call it E, is then given a tau rigid pair U living inside a wide subcategory V. Then there is a bijection between those tau rigid pairs X, which are compatible with U in the sense that X plus U is also tau rigid, and the tau rigid pairs in the tau perpendicular subcategory of U. Right? So there's a bijection between this and the X's which are compatible with U as tau rigid pairs. So this was the fact that there is such a map was proven actually in the setting of all finite dimensional algebras in the joint work with the joint paper with Bethany, or actually it is in, yes, it's in joint paper with Bethany that there is such a map for all also in the not necessarily tau rigid case. Right. And then the second fact is that, well, this map sort of behaves nice with respect to direct sums. So this formula might look strange. I will not try to explain it in detail. It basically says that if you want to, this is, by the way, it's a sloppy version of the statement. So this is true for so there's a one-to-one correspondence between in the composable X with this property and in the composable X, which are tau rigid pairs in the tau perpendicular. And furthermore, the map is additive in the sense that it then also provides bijections between those X's with, say, which has are direct summands, has two direct summands with the same X here with two direct summands, and so on. Right? So, but basically, important thing is that it works especially for indecomposable objects X. And then if you want to take direct sums, so if you take U plus V to be a tau rigid pair, then this factorizes in the following sense. So we can first take EU of V, which is just this map, and then EU of V is an object which lives inside this wide subcategory. EU of V lives inside here. So we can consider this map again, going then one step further, namely to this subcategory. Yeah. Okay, so the third nice property that this construction have is that when we take the tau perpendicular of a direct sum of U and V, where U plus V is tau rigid, then we can do this by first taking, so we do this in two steps. We first take J of U, so the tau perpendicular of U, and then this EU of V lives inside J of U. This EU, it lives inside, yeah, here I should say, sorry, I should say J E of U, just a second. Like this. So EU of V lives inside here, and then we can take the tau perpendicular of this object inside this category again, this, which is a smaller wide subcategory than V, right? So let me make two notes. So this identity here was proved in the joint paper with Bethany. Actually, it was stated only for tau rigid finite case, but the proof also holds in the general case of any finite-dimensional algebra. But in the paper with Eric, Eric found a nicer, shorter, a way to make the proof more efficient. So there's a shorter version of that proof. Basically, the problem with this map here is that it's not functorial at all. So it's described in terms of different cases. And then when you want to try to compose these things, you have to discuss a lot of different cases. So our original proof here is is quite long and tedious, and it was, but in the paper with Eric, it is a shorter version of the same proof. But the original proof also holds in the general case. While this statement here, it is quite easy in the tau-rigid case, tau-rigid finite case. So there, to do this in the general case, a new proof was needed, and this is in the paper with Eric. So this identity here. Okay. So this might look like strange formulas. I will now try to explain why this formula is sort of gives us composition for free. So now we want to compose two maps. So we have a tau-rigid pair U in W, and we have a tau-rigid pair T in W prime. What does this mean? So then this means that W prime is actually JV of U, because all maps are of that form. They are from V to JV of U. Right? So that's exactly how maps are formed in this category. So now T is a tau-rigid pair in this category. So then that means that W prime, double prime, it is by definition J of T, but J inside that smaller, inside J of U. And again, this J of U should be J V of U, the same as here. It should be J V of U. So that's one description of W. W double prime is this. This is what we get from first taking U and then T. We get this. But now this T, this step 1 here, it tells us that this T can be lifted uniquely to some V. So this T is actually T is EU of V. That's what we get from step 1, right? So if we just insert that here and then use our formula here, yeah, and this T, this V is compatible with U in the sense that V plus U is a tau-rigid pair, right? Then this formula 3 here tells us that what you get here when you compose is actually also the tau perpendicular of U plus V, where V is the pre-image of T in the map E. Right. So that means that you can define the composition here now as just saying it's JV of U plus E. Right. So that's the idea of getting a composition on this map. The essential point is somehow to have this way to relate tau-rigid objects in this smaller subcategory with tau-rigid pairs which are compatible with the U that you start with. Okay, so then this gives us composition, and then actually one can show, this is not obvious, but if one analyzes this a bit further, this formula gives us associativity almost for free. Right, so the essential point in proving that this is well defined, so that we have associativity, is actually proving that this map is well behaved with respect to sums. That's the idea. Okay. So let me see. Yes. So that's the main steps in the construction of this category of, but a category which has objects that are perpendicular wide subcategory. Then I think I want to end by maybe a commercial section saying that, well, there is much better way to do this, all this, our main problem here was the lack of functoriality of this map here, which causes a lot of problems in the sense that you have to do a lot of computations to discuss various cases, and it doesn't really behave very nice. So there's a recent paper by Børve. So it appeared on Archive last month. He constructs this category W in another and smarter way by instead looking at subcategories of the derived category. So all this now happens in the triangulated setting. In its most simple form, the idea is to replace tau rigid pairs with two-term pre-shifting complexes, and this idea was there already in the paper by Adachi Yama-Reiten. If you have such a pair where M is tau rigid, P is a projective which does not map to P to M, then you can take this thing, which is just the projective presentation of M. You puncture it and you draw out M, and then you add P, and then here you add the zero map. Then this is a so-called two-term pre-shifting object, basically just meaning that there are no maps. If you can think about this as a complex in the projectives, and there's no maps from this complex to the shift of this complex. So that's the concept of a pre-shifting object. Now the idea then is basically to look at the TIG subcategory generated by this and then localize with respect to this instead of forming these perpendicular subcategories. There's a lot of machinery there, a lot of technicalities, but the upshot is that in the end, this way of reducing, instead of reducing by taking to a perpendicular category, you reduce by doing some localization, which is something functorial and nice. And then in the end, you can replace this map, this associativity, this map with something which comes from localization, and then associativity is just a result of that the whole construction is functorial. So that's so then it can show that this gives an alternative approach to construct the same category, and it also then can be done much more general because one can deal with various other nice subcategories of triangulated categories. So it's in addition to giving a simpler way to prove things in our setting, it also gives a more general setup for constructing such categories. Okay, I think I will end there. Thank you very much for your attention.
Thank you very much for the beautiful talk. Any questions for the Zoom audience? You can type them in the chat and let me process. Okay, Ralph, go ahead.
Can you hear me, Aslak?
Yeah, I can hear you.
So you said these wide subcategories always come from are always realized as a module category. Is there a way to construct this lambda prime from lambda by some, I don't know, taking a quotient or?
Not all wide subcategories, but these functorially finite ones are module categories. Okay. Yes. I don't know if I understood what. So not all wide subcategories comes from our module categories, but the functorially finite ones are. And yes, whether you can construct this in another way directly from your original algebra, you mean? Is that what you ask, or?
Well, if you know what this algebra is already, because you have your functorially finite wide subcategories, then are these two algebras then related by some?
Yeah, okay, yeah. So there's a explicit construction of this in Jasso's paper. So basically what the way it is constructed is by first taking the so-called Bongard's completion of your tau rigid module. You take the endomorphism ring of that, and then you mod out the part which comes from your original module M, your tau rigid module M. So it's a factor algebra of an endomorphism ring of the Bongard's completion. So there's an explicit construction of that, yes.
Thank you. Brittany?
I have a question. Can you hear me?
Yes, I can hear you.
Okay, great. So you mentioned this short group in the key points slide, just the previous slide.
Yes.
The result you need for associativity.
Yeah.
So how does that work? Can you avoid doing this case by case as we did?
You're thinking about the point 2 here, the slightly shorter proof than the one.
Yes.
Yes. It is basically the same idea. It's just a more efficient way to do it. Yeah, it is. It's not radically different. It's just more efficient.
It's still case by case.
It still involves some discussing cases. Yes.
Okay.
Yes.
Okay. Thank you.
Matthew?
And to ask just a very quick terminological question. This localization on the last slide, is this an instance of what people call universal localization? Marks-Stoviceck. That's defined with a set of maps between projectors. Here you have one map between projectors. So there is a universal localization. I don't know if it's this.
I'm not sure about that. I mean, this is Verdier localization in a triangulated category. I'm not sure what is meant by universal localization in this setting. Sorry.
Okay.
Okay, any other questions?
I have a question.
Yeah.
Okay. So actually I have 2 questions. So the first question on this slide where you characterize the tau perpendicular white categories. Yeah. So somehow, can you say how this torsion class is obtained, or how? I mean, what is the relation between the torsion class and the white subcategory? I mean, if it comes from a tau rigid. I mean, if the white category comes from a tau rigid pair.
Yeah, let me see. So one way to think about it, at least, let me see. So this is basically, let me see, this is a torsion class.
I see.
This is a torsion-free class. So that's sort of a starting point of that.
I see. Okay, and then you go from there. I see. Okay, and then the other question I had was, okay, so you have this new category W. Do you know anything about it? Like any properties?
So you mean the category of tau perpendicular white subcategories? No, we don't know too many properties about it. It is well defined. We're happy with that. It's a good start. It's a good start.
Okay, interesting.
And there are sort of topological properties of it, which is used. I mean, in the tau rigid finite case, for example, there are some. So in the paper by Hanson and Igusa, they prove things about this category, which are useful in using it for describing the for sort of ending up with picture group relation to the picture group. For example, I think the concept of cubical category turns up there. So don't ask me for the definition there, but it is in the paper of Hanson and Igusa. Yeah. So in that sense, there are some known properties. Yes.
Okay, thanks. Very nice talk. Thanks.
Thank you. Any other questions? I don't see any in the room and I don't see any in the chat. So let's thank Aslak again for this talk. Thank you very much, everyone, for joining. See you next time.
Thank you.
Thank you, Aslak.
Thank you.